Hi folks, Max and Phil here, and today we're going to be answering the question, why do birds migrate? The reasons for bird migration have been hypothesized about for generations. Records of bird migration exist from 3,000 years ago in writings by Aristotle and Homer. In addition, bird migration is mentioned in the Bible. Doth the hawk fly by thy wisdom and stretch her wings toward the south? Book of Job 39:26. An interesting thing about this quote is that the migration of birds primarily occurs in the northern hemisphere flying south, so this particular quote from the Bible is actually very accurate. In order to understand why birds migrate, we must attain an understanding of what migration means. Migration comes from the Latin term migratus, which means to change. In English, migration is defined as the seasonal movement of animals from one region to another. Not all bird migration is the same, however. There is short distance, medium distance, and long distance migration. Medium distance migration, indicated by the shorter red arrow, occurs over several states or provinces and rarely over whole continents, whereas long distance migration can span over entire continents or even more. Indicated by the green arrow is the migration pattern of the Arctic tern. The Arctic tern in its migration from the Arctic to Antarctica each year travels some 22,000 kilometers. On the polar opposite end of the spectrum, we have short distance migration. Short distance migrants stay within their original environment. An example would be moving from higher to lower elevation on a mountainside. Moving to lower elevation would allow the bird to find better nesting conditions and more food. An example of a short-distance migratory bird is the wall creeper.
But biologically speaking, how do birds know when to migrate? There are a couple of factors that influence the migration of birds. Environmental and physical factors both have this effect. The length of days and the seasons are associated with the changes in temperature, and these two factors alert the bird on its changing environment. This causes hormonal changes to the bird's endocrine system, alerting it that it's time to migrate. In order to make these large-scale migrations work, a bird has to think of its own energy consumption and its own energy conservation. Therefore, they usually stock up on 25 to 40% of its original fat deposits to have enough calories for the entire trip. When people think of flying birds, they often associate it with a V. Well, this V formation is also a form of energy conservation. It involves the concepts of aerodynamics and the benefits of free lift to the birds behind the leading bird. But let's get into the physics behind this. The V formation is executed in such a way that whenever the leading bird at the front of the V is tired, it can return to the back of the V and use less force to stay in the air. We ask ourselves why and how this formation affects a bird's ability to conserve more or less energy depending on its location in the V. Well, to answer that, let's venture into the mind of a bird and understand its instincts. The whole concept of aerodynamics applies to this formation. Look at the wings of a plane and ask yourselves where the lift is coming from. The constant downward force of gravity is pulling the wing down at an acceleration of approximately 9.8 meters per second squared. But we're still looking at the large-scale perspective. Let's magnify our situation to the molecular level and really understand how the plane just doesn't drop. The answer is in the molecules of air. Lift is a result of air from the underside of the bird pushing against the bird to hold it up in the air. However, when air is pushed away from the underside of the bird, it will create a wingtip vortex. This wingtip vortex will move air back onto the wing, which will act as a negative factor affecting its flight. Here we have upwash and downwash. It is essentially free lift for any object near the vortex, and it applies to the V formation. Let's understand how these tiny molecules are affecting the wings of a bird and the lift it's experiencing. When a bird flaps its wings downwards, it's compressing the air underneath its wing, and since air is abundant, it'll have the tendency to either move downwards or seep over the corner of the wing back to the top of the bird. This means that while a bird is generating lift with one wing, it's also creating a slight negative force on top of the wing. This means that as a bird is flying, it's generating its own lift, but the downward movement of the wing is also generating a negative lift. Now let's apply this concept to the entire V formation. We took a picture of a plane to demonstrate how air is moved from the bottom to the top of the plane, or the bird in this case. Throughout the demonstration, the plane will be the front bird, or the front of the V. To its sides we'll have the two other birds which will demonstrate how the lift is affecting their flight pattern. Here we have what is known as the wingtip vortex. The two birds on the side of the main one will experience an upwash, known as free lift. However, as we've previously established, there's a negative lift experienced by the bird at the front. As the vortex on the front of the bird moves back to the top of the wing, you experience the downwash. This means that the birds on the side of the V will always experience free lift, known as upwash. However, the bird at the front will experience a downwash and consume more energy than normal. But there is a benefit to this. Although the front bird uses more energy, it is giving free lift to the birds on the side of the V. So to recap, the birds conserve energy by using the V formation to conserve energy in their flight. This is essential for long-term migrations, as large distances require large amounts of energy. So the wingtip vortex isn't so bad after all. It's the main reason these birds can undergo these large-scale distances without using as much energy. The upwash generated for the birds on the side of the V allow them to conserve a lot more energy than usual, and although the front bird is consuming more energy than usual, it can simply move to the back of the V and conserve more energy once it feels the need to. But what about direction? How do birds know where to navigate and where to migrate? Scientists have come up with multiple theories to explain these internal compasses that most birds possess. The first being natural selection. For example, take a look at a bird on the east coast. Those who decided to migrate north generally migrated to colder temperatures and died off. Those moving south migrated to warmer temperatures and survived. Those moving east migrated to the ocean and probably never found land, while those to the west might have encountered food shortages. Therefore, the only ones who survived were probably the ones moving south, and that instinct stayed with them. The next two theories involve light and magnetism, and how birds use these two forms to navigate over the course of large-scale distances. How do birds sense and respond to the magnetic fields of the Earth? Well, all animals contain the molecule iron 3 oxide in very small quantities throughout their body, and therefore the magnetic fields of Earth and these small molecules have a slight interaction which affects the bird's ability to sense its direction. And due to the interaction, the neuroreceptors in the bird's brain will pick up on the slight influence over the iron oxide and give the bird a sense of the right direction based on the magnetic fields of the Earth.
Another way in which birds know where to migrate has to do with light wavelengths. Laboratory experiments have shown the magnetic compass to be wavelength dependent. When light enters a bird's eye, it causes certain compounds within the bird's eye to change. These changes result in chemical signals being sent back to the brain, which the bird interprets and then uses to orient itself. An example of this would be nocturnally migrating birds who use green light wavelengths in order to help them migrate. Blue wavelengths of light are thought to be special, because they could be the cause of quantum entanglement within a bird's eye. Now the question many of you are asking is probably, what is quantum entanglement? Quantum entanglement is a physical phenomenon that occurs when pairs or groups of particles are generated at the same time and interact in ways such that the quantum state of each particle cannot be described independently. Instead, a quantum state may be given for the system as a whole. For example, we know that two electrons in the same orbital are supposed to have opposite spin numbers of 0.5 and negative 0.5. However, while they are entangled, it is impossible to tell which way each electron is spinning. The only way to measure the spin is if they are to be unentangled. If they are to become unentangled, in that exact same instant that one electron's spin is measured, the other electron will automatically have an opposite spin. Otherwise, it would violate the fundamental laws of physics. Now, relating back to the original topic, what does quantum entanglement have to do with bird migration? The Earth's magnetic field would alter the alignment of electron spins and in the process alter the chemical properties of the molecules. Physicists suspect that the reactions would leave varying concentrations of chemicals throughout the eye, possibly creating a picture of our planet's magnetic field that would allow birds to orient themselves. A chemical called cryptochrome, which is located within the bird's eye, is being studied for evidence of quantum entanglement. It is thought that electron pairs entangle within the cryptochrome within the presence of blue light. Well, that's all for today. Hope you enjoyed the video and thanks for watching.